Let's now take a look at this review problem. A die is rolled 4,000 times. Find the probability that we get at least 700 sixes. And in this problem we will be using the calculator to do the calculation of for the bell curve. For now, let's see, we have the probability that x is at least 700. Now I'm going to use the bell curve for this problem, and the bell curve applies because I have a large number of trials. My large number of trials, I have n is equal to 4,000, and also my probability of success is going to be equal to 1/6. That's the chance of getting a 6, of rolling a 6, when a fair 6-sided die is being rolled. So I have a large number of trials. Also n times p and n times 1 minus p are both greater than 10, as you can quickly confirm. And so the normal approximation does apply to this. Okay, so to do that I need to first you apply the continuity correction. So when I apply the continuity correction, the picture is 700, then 701, 702, and I pretend I have rectangles on top of these that correspond to the binomial distribution from which this comes. So x is greater than or equal to 700 because the question says at least 700, so I have an equal sign there. So I include the rectangle on 700 and I'm going to the right. And therefore the left endpoint of the leftmost rectangle will be at 699.5. So I can write this as equal to the probability that x is greater than or equal to 699.5. Now let me mention before I continue that I only do this continuity correction when I have a counting problem, where I'm counting the number of successes and I'm approximating either a binomial by the bell curve or else I'm approximating a hypergeometric by the bell curve. So that is the case for the purposes of this class, that I will do this 0.5 business, either 0.5 up or 0.5 down. If the problem, like some others in this review, simply says that x is normally distributed, then because x was given to be normally distributed in the first place, then there would be no correction. However, in this problem, the original x is binomially distributed. It's discrete, and so therefore I need to make the correction. So I want to mention that parenthetically before we continue. Okay, now I need to convert this to standard units. So that means I need the mean mu, which is equal to n times p, and in our case 4,000 times a sixth, which works out to be 666 2/3. The other thing we need to do is to convert to standard units is the standard deviation. And for counting problems, we have sigma is equal to square root of n times p times 1 minus p. So that's equal to the square root of 4,000 times a sixth times 5/6. And punching into the calculator, that's approximately 23.57022. Okay, so we have that this is equal to the probability that a standard normal random variable is bigger than or equal to 699.5 minus 666 2/3 divided by the standard deviation of 23.57022. Okay, so the probability that z is at least equal to. Okay, so let's pull this up and do the computation. So let's first do the square root by itself. Square root of 4,000 times a sixth times 5/6 is the 23.57. And so when I convert to standard units, 699.5 minus 4,000 over 6 divided by the answer we just got gives our answer in standard units, 1.393. And so our final answer is going to be the area to the right of that mark. So the picture is going to look like this. There's the bell curve, 1.3 is here, and I need the area to the right. And so using a TI calculator, we would do second distribution, go to normal CDF, and I want the area between that number and plus infinity, and I will use 10 to the 99 for plus infinity. So that is the answer, and so I get the area under the curve to be equal to 0.08181. I believe that's right. Let me pull the calculator back up to make sure. And that is the answer to 5 decimal places. So that is the calculation. If we used Microsoft Excel, then the command would be 1 minus norm s dist of 1.393 to find the area to the right. Using Microsoft Excel, norm s dist returns the area to the left, and so 1 minus norm s dist returns the area to the right. So that is a probability of about 8.2%.